Hello everybody again, and welcome to the second lecture in the course of Construction of Electronic Systems. Today we will talk about printed circuit board technologies. The printed circuit board technologies are important for every PCB designer to understand, because this is a material with which the designer is working with, and knowing what are the limitations of these PCB technologies and what are the advantages and price points and so on is very important. So every time you are working with the design of a new, rarely unknown PCB technology, you have to be in contact with the PCB producer to help you out with all the details you have to know. Right? So, and this is another reason why somebody should know what PCB technologies are all about. Okay, this is the main outline of this talk. We'll talk about different technologies, but those which are bolded are the most important ones. So the first technology is the simplest technology, called simple PCB technology with photomasking. What does it mean? Well, the simplest PCBs are usually single-sided PCBs, and they are usually structured with photomasking technology. So the base material is copper clad laminate called. So it's a laminate material covered with a thin copper line. So what we do next, we apply photoresist on it. That's the photosensitive layer. And then we mask it with some illumination technique so that copper is protected. And then we etch the rest of the copper, which is not protected. And then we get this photoresist off, and finally we'll drill the holes. So that's the simplest procedure for the most cost-effective PCBs. The limitations are that it is, I would say, limited to single and double layer PCBs, and that the holes are not conductive. And that's the main limitation of this PCB. However, if we are using through-hole components and a single layer PCB, then the non-conductiveness of this hole is not an issue here. Okay. Here is a little bit more in detail describe this process. Here we are representing you the double layer process with exactly the same procedure. So applying photoresist, then applying UV light or shining with a UV light through the mask. This is called positive mask because the layers which are actually seen on the mask are the layers which are not illuminated, and these are the photoresistive layers that stay intact, and the illuminated layers are then removed. Then we do the etching of the copper. The etching is usually done with the 3 different options. The most used is combination of hydrochloric acid and the peroxide. It also, you can use ferron chloride or natrium persulfate. However, this is the most used here. Then we remove the photoresist and we drill the holes. So that's it. You can do it at home if you have the chemicals, and all these chemicals here can be bought easily. The natrium peroxide is also, natrium hydroxide is also used for developing the photoresist. I forgot to mention that. So natrium peroxide you have to buy, and you have to buy the hydrochloric acid and hydrogen peroxide. You can all that buy in any market that sells home domestic use chemicals. However, this process is not really, how to say, convenient. I mean, having these chemicals at home, and some of them are a little bit dangerous to use, and they smell and so on. it's not very convenient. And UV light, for example, it's also, well, you can buy a UV lamp and you eliminated it, but it's not, I would say, the most safe thing to use at home. So there is another option which is quite popular nowadays with home users, and this is simple PCB technology with toner transfer. What does that mean? Well, you have the same laminate, and then you print the mirror image on a very smooth and waxed paper foil. Then you attach it to the PCB here. I have to switch now. Then you attach it to the PCB here, and then this toner is transferred to the copper. And then you etch the copper, you strip the toner off, and you drill the holes. That's quite easy procedure you can do at home. And I must say that a lot of people are actually using it, but not for professional production. In professional production, normal procedure with UV light and all the photoresistive approach is used. Then what we also use in our lab is mechanical milling and drilling machine. So there is a machine that with a spindle and a drill, it takes off all the extra copper and isolates the tracks. So this is how this machine looks like, and I hope we'll manage to play it. So it drills and takes away the extra copper and makes the PCB. It takes a little bit of time, but it uses no chemicals, and it is environmentally friendly, I would say. And you can make a small PCB in a matter of half an hour. Then you test it and again repair or make changes and do it again. So that's quite used system. The data for such a machine are quite, I would say, accurate, but reaching this minimum track width and isolation width is quite hard. Usually you have to multiply these numbers by 2 and then you can make it easy. So 0.2 millimeters, it's not a hard thing to do with this machine. You can also use laser structuring instead of mechanical. And this laser structuring, of course, is expensive, but you can make finer, smaller features. For uneven surfaces, you can also use 3D laser structuring. The 3D laser structuring is done by laser, of course, and it can be applied to different surfaces, making some circuits on housings, antennas, and so on. It's not the most cheap one, but you can read more about it here on this link. I didn't see pretty much use of it. Now we will go to the mainstream. Which is the production of a multilayer PCB with metalized vias, which is the most used and most, I would say, common procedure that is done nowadays. Okay, let's start. So, multilayer PCB technology. I'm showing here a 6-layer PCBs. At the beginning, what do we have? We have two 2-layer PCBs, and these 2 double-layer PCBs are all made with the simple technique shown at the beginning. Then we put isolator in betweens, which are called pre-preg. I suppose you remember what a pre-preg is, a pre-impregnated cloth. And then we put 2 layers of copper sheets on both sides, and we put this stack together and press it. By that we make an initial stack that will be then processed. Then we drill the holes. The important thing is that the holes are drilled at the beginning. So we drill all the holes, and then we apply so-called electroless copper deposition. This is also called a black hole procedure. What does that mean? It's a copper in a solution is applied to all surfaces and without any electrical current, because the PCB at the beginning is not metallized here, so the copper has to attach to all non-conductive surfaces, and this is done by this electroless copper deposition technique. And then at the end of this step, all the surface of the PCB is covered with copper, very thin copper, maybe micron or 2 microns thick copper layer. Then we mask it, but with this time we mask it the opposite. So we expose with UV light, and the copper or the photoresistive layer we use is a negative layer. That means that the parts that are exposed are actually binded and stay, and the parts which are not exposed are removed. So by that, it's the opposite as we heard at the beginning. By that, the openings are left for the tracks. And the next step is galvanic plating of the copper, and then protecting this copper with a tin. Well, why do we do that? The thing is that we have to metallize vias, so the copper has to be attached or deposited in the vias as well, and it should be adequately thick. That's why at the beginning the copper layer is the thinnest we can get, and then we reach the final copper thickness with additional electrical plating. And because at the beginning the PCB is already already plated with the thinnest copper layer at the beginning here with electroless copper deposition, then all the PCB is conductive, so we can apply electrical copper deposition with electrolyzers, and this then reaches the final copper thicknesses at all places where needed. So that's why we use the negative technique here to open the spaces for the extra copper. And then we cover it with a tin to protect it from the etchant. Then we remove the photoresist and we etch it. Etching is done with ammonia etchants, and this is quite smelly, as you can imagine. At the end, we remove the tin as well, and this is the PCB we get. We have vias, we have copper layers, copper tracks, and we have metallized vias, which is the basic and most important step to make metallized vias. With that, we can make multi-layer PCBs. Then we apply the solder mask, the green thing, and we leave the opening where the soldering will be done. And then we apply surface finish into these openings. So by that, we protect this open copper area, exposed copper area, from the environment. Then we print the silk screen, so the component designators, all the text, all the graphics, and that's it. We do then the electrical test of the PCBs. This electrical testing is done to check for the conductiveness and for the isolation between different layers and tracks, and this is done automatically. And finally, we cut the PCB into a certain desired shape. Yeah, quite a lot of steps now, but quite a lot of additional steps, because the main focus here is to make metallized vias. And maybe just to make sure, the first simple process to make a single or even double layer PCB without metallized holes was just removing the extra copper with etchant. So etching the copper, and the final copper, the thickness of the final copper is equal to the thickness of the copper at the beginning, because we just remove it. But here in this multilayer metallized vias PCB process, we have to start with the thinnest copper layer possible. This is from 9 to 18 microns or so. And then we electrical plate the PCB to make the final copper thickness. So that's one of the differences between these two procedures. Right? What about the metallized vias? What is the thing here? We have three types of metallized vias. First is a classical through-hole via. That's this one here. Then we have blind vias and buried vias. So blind vias are vias which are seen from the outside, and buried vias are those which are inside the stack and you cannot see them outside. So that's, I would say, quite a thing here. I mean, you have to know that buried vias here are the most expensive ones, and they are hard to detect if there are any errors. So let's go further. Let's go a little bit into this detail. These metallized vias, of course, the most, I would say, cheap ones and used are, of course, the classical through-hole metallized vias. Then, if you want to make a little bit more space, because if these vias are all through the stack, then they take space even if they were connected just two layers from inner in the PCB, two inner layers. Then, of course, you can save space by making blind vias here. But then you can connect from surface to a certain layer inside. But making buried vias, that's of course saving more space on the outside, but you have to sacrifice quite a lot in terms of procedures and price as well. Okay, so this is classical through-hole via. If this through-hole via is intended for soldering, for example, if this is used for a through-hole component, then it should be connected with so-called thermal relief to the extra copper outside, to the copper layers, because by that you actually prevent the heat to be transferred quickly away from the soldering point. What about the other vias? Well, the inner vias, the buried vias here, are always between layers that are part of a stack. So this, let's say, is one single double layer PCB that is later pressed into the final PCB, and this is achievable. But you cannot make a buried via between this and this layer here, because then, of course, this wouldn't be possible just by taking a double layer metallized whole PCB and stack it together. The blind vias, of course, as I said, can connect the surface to a certain layer inside. But there is a catch here, and I will show it later. It cannot be deep as you want. There are quite a lot of limitations. Okay, micro vias. What are micro vias? Micro vias are all vias that are small. Okay, I would say smaller than 150 microns in diameter. Maybe even smaller than 100 microns in diameter, I would say nowadays. And they can be made by mechanical drilling with the very special drills to a certain depth, or they can be made by lasers. And lasers actually are quite useful for this type of vias because they can be made in so-called self-adjusting manner, which means that the copper acts as a shield or a reflective surface for the laser. So the wavelength of the laser is chosen in the way that the laser is reflected from the copper, but the FR4 laminate absorbs the power and it gets removed. So just by preparing the copper layers, you can define the width and the depth of the wire, as shown here. And this is how the micro vias look like in reality. So, yeah, quite nice, aren't they? So, micro vias are a good solution to make very small blind vias that are made from the surface to a certain depth. However, they cannot be made infinitely deep. The thing is that here, if the via is not a through-hole via, then it is so-called trapped from 3 sides. Only one side is open, and a small bubble can be formed inside. So the via, if it is, I would say, wide enough and narrow, there is not a problem. But if the via is deep and narrow, then it is a problem, because the bubbles cannot get out of some air bubbles or some other gases. And if they are trapped inside, the via can be damaged, or it cannot even be formed. So you cannot make very deep and very narrow vias. And of course, the main advantage of micro vias, of course, is that are narrow and small. And this is quite a problem, and I will show you later. Final, let's go further. Final technology I would like to show is so-called high-density interconnect technology. Well, it's more or less a demonstration of all this technology I've shown you, with some extra things to be, I would say, pointed out. So an 8-layer high-density interconnect PCB technology is shown here. So this is an 8-layer PCB. I took all these images from my colleague Gregor Čoruch, who works at Intec2 company, Slovenian company that produces high-density PCBs. And he gave me the, I would say, green light to use his slides here at this lecture. So this is a example of this high-density interconnect PCB. As you see here, it has 8 layers, the top and bottom front layer, surface layer, and 6 inner layers. And these are micro vias that are I would say, one layer deep here on top and bottom. This is a buried via, this is another buried via, and these are through-hole vias. So how is this PCB made? As you see, it will have quite a lot of steps. So let's start. Let's start with the base laminate. We start with the middle layer, layer 4 and 5. So this is a 2-layer PCB, simple 2-layer PCB. And how is it made? Normally, as I shown you before, the advanced procedure for metallized vias. And I will make it a little bit shorter. So we'll drill holes. We copper plate the holes and surface, of course, with electroless copper deposition and then the electrical deposition. Then we fill all the holes with non-conductive paste, and then we etch. So at the end we have metallized vias and etched lines. Continuing, we just do the same thing with layer 2 and 3 and layer 6 and 7. So again, drilling holes and etching, but in this case, as you see from this picture, no buried vias are between layer 2 and 3, and no buried vias are between layer 6 and 7. So we don't need any electrical plating, and we don't need any drilling. So we just etch. So that's, I would say, for these 2 layers and that 2, this is the simple procedure without metallized vias. The first procedure I've shown you today. So then we add prepregs, 2 prepregs for isolation, and then we align the stack. As you see, the stack is not aligned. Let's say if these tracks here have to be aligned, so we align it. So how do we align? Well, you have to have some sort of a optical mechanical system that automatically aligns the layers to be perfectly on top of each other. And then we press the stack. So this is first pressing. We press the stack, and that stack got, I would say, sticks together and forms a new PCB with 6 layers. And then we have to make this hole here, that one. So we drill the holes, we do the copper plating, we do the filling of this hole, and then we do the etching. So why do we fill the hole? Because then the etchant cannot enter and cannot be trapped inside. So now the outer layers are etched, the holes are metallized, so we add additional 2 prepregs, we add final copper layers, final copper foils, and we press again. Now we get the final stack with the final thickness. Then we drill the micro vias mechanically or with laser. We copper plate again. We fill the holes with non-conductive paste. Again, we drill the through-hole vias, and here are the dimensions. Usually the smallest dimensions for vias are 100 microns, micro vias, and a little bit more for the through-hole vias. Now, what you can do, again, you can copper plate the through-hole vias. These are the dimensions again. And you etch the outer layers. So now the final outer layer, see here, is etched. Now the thing is that now this via is not filled with non-conductive paste because it should be exposed, maybe for some through-hole components or whatever. So before we finish, we apply solder mask, these green layers on top and bottom, which expose the opened areas for soldering. And then we do the final surface finish. So the areas which are open in the solder mask are then covered either with hot air solder leveling, HASL, or surface copper plating, gold plating with so-called electroless nickel immersion gold technique. Usually such a high density PCBs are more or less using INIG because it has longer shelf life, better stability, and so on. And we cut the PCB. So that's it. Quite a lot of procedures. And yeah, this makes such PCBs quite expensive. I would just like to show you another 8-layer PCB which uses 3 times the pressing, because somebody said, okay, I would like to have through-hole vias, I would like to have 2 thickness or 2 depths of micro vias, and because the micro via of such dimensions cannot be made twice as deep because of this bubble trapping problem, they actually make it twice. So they make it here and again one on top of each other to make 2 micro vias stacked one on top each other, and then it makes together vias with double the depth. Now that of course requires 3 pressings. So when you decide what kind of connections you would like to have between the layers, that's the reason, or that's the consequence. And sometimes, let's say here, you have through-hole vias that are connecting front layer, front surface with the 5th layer. Now, how would you do that? Would you go rather with 1, 2, 3, 4 microwires? Maybe you can do something else. Maybe you can just drill from the backside to this step and then make the connection at the end. This is so-called back drill process. Sometimes in really high frequency PCBs, this back drill process removes the excess copper of this through-hole wire for signal integrity problems. At high frequency connections, you want to avoid all parts of your copper that are taking you nowhere, that are, blind. And making 5 microwires on top of each other is a no-go. So you rather make the through-hole wire and you then back drill to remove it later. So how does this 8-layer PCB then look like at the end? You see here layers on top, layers on bottom, the 2 microwires, connection of inner layer. This is a 6-layer PCB, as you see. Through-hole wire, and see here microwires that are connecting the blind wire in between and another microwire here. That's a really, really expensive and very complicated PCB. Now I would like to take you to a final part of this lecture, which is how to define layers in Altium. This is a picture from Altium Designer. We have so-called layer stack manager, and in this layer stack manager you define the stack. This is an example of a 4-layer PCB, and rather going through the slides, I would rather take you directly to Altium. So that's the Altium Designer PCB. So I would rather show it a little bit larger. So the Altium Designer PCB, this is a 4-layer PCB. In 3D it looks like that. And yeah, nothing really special, I would say. So let me show you the layer stack manager. You go here, design, layer stack manager, and you would eventually see it, I suppose. Okay, so that's the layer stack manager. And here you can define the layer stack properties. And you have to check your producer, what kind of layer thicknesses he actually allows. What does it have? And let me go to some producer and show it to you. So this is a web page from one of the Chinese producer. It's quite popular, JLC PCB. And here it shows you the dimensions he can make and also the stacks that he offers. So 35 micron outer layer, 0.2 millimeters, 17 microns inner layer, 1 millimeter, and a little bit more, 70 microns, 0.2 millimeters, 35 microns of copper. Or then you can make only 100 microns of the prepreg. Here it's 200, here is 100, but then the inner layer is thicker, and then again, and so on. The same thing for the 6-layer and so on. So by that you can choose what the producer can make, and you define this layer stack. And if you go to the layer stack visualizer, you see it in 3D maybe. It's a little bit more easy. The dimensions are not correct here. You have to go to the real layer heights to actually see how it looks like in reality. So see here, you see a through hole, the top layer, bottom layer, and the mid layers. And this is the inner PCB, and then 2 prepregs. And yeah, how you define the layers is shown here. Of course, you can define also the vias. You click to the via types, and you can add vias. So you can have classical through-hole vias, then you can add another via, a blind via, you can add another blind via, and you say, okay, I want to set the properties of this via. Where are the properties? Yeah, okay, it will start at maybe third layer and stop at fourth layer, and so on and so on. You can really complicate it hard. All right, then what about the PCB itself? In Altium, you have several layers, and you have to know these layers. What are they for? So I can show here all the layers separately. So this is the top layer. It's called top layer. Sometimes it's also called the component side, because in old times on the top layer there were components, but now it's not the case anymore. Then the bottom layer, or the solder side. And here are the mid layers. Here are called signal layer 1, signal layer 2. If you had several mid layers, you would call them as according to their number. So here you see these are on the mid layer, this is on the signal layer number 1, this is the top layer and the bottom layer. So these are 4 layers that are actually defining the copper features on each layer of the PCB. What do we have extra? We have so-called top and bottom solder mask. The top solder mask and bottom solder mask are the openings in the mask where the components are soldered. So where the pads are, like here. These are the mask openings in the mask. So top solder for the top layer and bottom solder for the bottom layer. Then we have top paste. These are openings for the paste application. So when you use you can use the stencil, and these are the openings in the stencil where you apply the paste. And then you have the bottom paste layer. Here no components are on bottom layer, so there is nothing on the bottom paste layer. And finally, what is also important for you is keep out layer. With the keep out layer, you define the shape of the PCB. And I think that's all you need to know, more or less, basically, about the layers in the PCB in Altium Designer. And this is all also defined in so-called layer stack manager. Okay, I forgot the top overlay. Yeah, top overlay and bottom overlay. These are all these prints, the signs, the text that is printed on the PCB on top side and bottom side. There is nothing on bottom side here, so no text is printed. And yeah, that's really it. So after this lecture, what you learned, I suppose you should be aware of or should know at the end, is you should describe the production steps of a simple one-sided photolithography process of the PCB, and of course the professional multilayer PCB steps. And you should know what are the consequences when you choose for a certain layer stack with a certain type of vias. So you should explain why is the buried via expensive than blind via, and what are the limitations of these vias, and how many steps is then required to make a certain type of the via. And of course, you should be able to choose the most appropriate procedure according to your application. At the end, here are some links. You can read a little bit more about these processes, and there are some links to the producers that are commonly used in Slovenia and worldwide. So by that, I will conclude this and see you again soon.